Okay, so the whole thing about dynamics is it's based on this very simple law, which is the Newton's law, right? F equals ma. There are three laws, but we just the one which is used for simulations is the second law. F equals ma, and the counterpart in the world of rotations is torque equals I alpha. A is acceleration, and alpha is the angular acceleration. Okay. So normally what happens is if you do this with Newton's laws, this is something which you might have learned as an undergrad in dynamics course. You first draw what is known as a free body diagram. Okay. Once you have the free body diagram, then you invoke Newton's laws, either F equals ma or torque equals I alpha. And then you solve. So given F, M, torque, I, you solve for A and alpha. Okay, that's actually called the inverse dynamics problem, which is you're solving for A and alpha given F and M, T and I. And then there's other problem, like just like forward inverse kinematics, there's forward dynamics, inverse dynamics. So that's the inverse dynamics. The forward dynamics is you find F such that you find F for a given kinematic, so A and alpha. Okay, so I think in general, people don't like free body diagrams. So what we'll do for 2D at least is we will not use Newton's laws. Well, we have to use Newton's laws, but we'll use it in a different form, so we don't have to really draw free body diagrams. There is this method called Euler-Lagrange method. And this method gives you the equations of motion without drawing any free body diagrams. Okay. Okay, so we will use get equations of motion without drawing free body diagrams. Okay, so I'm going to give you basically a recipe which you're just repeating for every problem in dynamics. The same thing we'll be doing. So here is the procedure. The first step is we need to write the kinematics. So in case of movement of bodies, we are interested in the motion of the center of mass. And so we want to figure out what is the position of the center of mass. Now for something which is a point mass moving in straight lines is just a position of the center of mass, very simple. But if it is, let's say that's a double pendulum, there are two links, then the center of mass has to be written in terms of thetas and lengths and so on, and that becomes a little bit more complicated. So we'll have to invoke, in that case, the forward kinematics, something we learned earlier, in order to find the position of the different points. So first is write positions of the center of mass and you always want to do it with respect to the fixed frame. Okay, so for example, if you have a pendulum, this is the center of mass, and you need to compute its position x, y, x, let's say x1, y1, x2, y2, and you can see that in order to do that with respect to this frame, you need to use some of the things we learned for the forward kinematics. We need to write those homogeneous matrices, then multiply them with the positions, and then we get the position of x1, y1. in x2, y2. So that's probably the hardest step. The second and third steps are actually very straightforward. The second step is to write the Lagrangian, which is L is T minus V. This is called the Lagrangian. The T is the kinetic energy, and V is the potential energy. So the formula for T is, if you have M and N bodies, you just write mi vi square plus inertia omega I square, where V is clearly the, so let me write all things down here. M is mass, I is inertia, Vi is linear speed, and omega I is angular speed. Okay, so writing that down is fairly straightforward if you now know the velocity. Sorry, you know the position. So if you know the position, you just take the derivative of position to get the velocity. That's why you need to first write the position. Once you have T, we can write V. V is a potential energy. It is V is again summation I equals 1 to N mi g I. And since we're living in the 2D world, I'm going to assume that x-axis is horizontal, y-axis is vertical. So it's typically the position of the y position of the center of mass. And I put 0 to indicate that it's with respect to the world frame, which is fixed. And sometimes if you have springs, then you should have something for springs. So this will be half of that. So there could be, I don't know, Q springs. So here, G is gravity, Y is Y position of center of mass, RP is spring length, RP0 is rest length, and Kp is spring constant. Okay, so we've got V, we've computed L because we know T and V, it's T minus V. And then the third step, which is the final step, is equations of motion. Are simply this thing. It's d dt of the partial derivative of dl with respect to dq. I'll tell you what dq is. dq dot, let's call that j minus dl dq j equals qj. Okay, qj is the degree of freedom. Okay, so for example, if you have a mass which is traveling in a straight line, qj would be just x. If you have a pendulum with angles theta 1, theta 2, then qj will be theta 1, theta 2. So you'll have two equations, right? Because you do this derivative for each j. So for the motion in a straight line, you'll have one equation. For a double pendulum, the 2 degrees of freedom, you have two equations. If you have a triple pendulum, 3, and so on. So this is basically the Newton's law. It's interesting that that complicated expression there is actually Newton's law, and I'll actually show you how it boils down to Newton's law for simple cases like ball and gravity, and then we'll do more complicated things. As an example, illustrating Lagrangian equations, projectile motion. Okay, so the problem is if you have a projectile, you launch it, it flies under gravity. So V, and then let's say that you launch it with Vx0 along the x-axis and Vy0 along the y-axis. Okay, now just to make life hard or complicated, we are going to assume that it falls under gravity, but there's a drag force, and the drag force is a quadratic drag. Quadratic drag force. Okay, the model for this drag force is that it is proportional to the square of the velocity, but we need to give it some sense of direction. So we multiply with this with a unit vector in the velocity direction. So don't worry too much if you don't know what unit vectors and all are. It's not really needed, it's only needed for this example. So the velocity is x dot square plus y dot square. And a unit vector is written as x dot I plus y dot j divided by the magnitude. So this should be that, and this should be x dot square. Okay, so the only thing you need to know is that, and of course, this is, I'll give you this, you don't have to know how to do this unit vectors and all that's not really required in the course. The drag force in the x direction is c times x dot divided by, sorry. So I'm just going to take the x component, which is everything in front of the I. So it's c minus c times x dot square plus y dot square times x dot, and f dy equals minus c times x dot square plus y dot square times y dot. Okay, so with that, let's just use that 3 steps of the Lagrange equations, Euler-Lagrange equations recipe, and we'll get the equations of motion. So first step, get the position of the center of mass. So in this case, it's trivial that the position is simply x and y, and x dot y is the velocity. We don't need to do any work there. Second step is get the Lagrangian, which is t minus v. T is 0.5. There's a single mass. Let's assume that its mass is m times v squared. Okay, so that's simple. The potential energy is mass times gravity times y. So y being the distance, vertical distance. Okay, so the Lagrangian is t minus v, which is 0.5 m x dot square plus y dot square minus mgy. And the last step is to use this equation, d dt j minus t. Okay, so let's use that and we should be done. So first we'll take qj equals x, right? There are 2 degrees of freedom, x and y, so we need to do it 2 times to get the 2 equations. So we write d dt of dl dx dot minus dl dx equals q qx. In this case, qx is f dx. Okay, similarly, we have d dt dl dy dot minus dl dy equals f dy. Okay, 3:15. Give me a minute and I'll be done. So we just have to now pretty much take the derivative of L. with respect to x dot and x, and y dot and y. Okay, so d dt of the derivative of that expression with respect to x dot. So you need to treat x dot as a variable, right? So x dot appears here, so it's going to be 0.5 m times 2x dot minus dl with respect to x. There's nothing here is a function of x, so that part is 0, equals f dx, so minus c x dot square root of x dot square plus y dot square. So when you take the derivative of this term with respect to time, you get 0.5 m. The 2 and 0.5 cancels off. So we're left with m x double dot equals minus c x dot. Okay, similarly, if you do the same thing for the y direction, you have d dt 0.5 m to y dot. Now, when you take the derivative of this expression with respect to y, mgy appears there, so it will become minus mg. That's the derivative with respect to y. So it will be a minus mg equals minus c y dot x dot square plus y dot square. And the last step is we have my double dot minus mg. Oh, my bad. This should be plus equals minus cy dot. Okay, I'm done. That's my first equation. The second equation, you might recognize the equations without the c. If you put c equals 0, you get the equations of a projectile with no drag force. Yeah, stop.
X double dot equals minus c divided by m times x dot square root of x dot square plus y dot square, and y double dot equals minus g minus c divided by m y dot square root of x dot square plus y dot square. Okay, so then maybe the last step is to simulate and animate in Python. Okay, for simulation, we need to do is we need to integrate the equations of motion. Equations. In the past, we've seen we have done this for the differential drive car with the Euler's method. That's one way to do it. Another way to do it is using the Runge-Kutta method. Okay, yet another way is to use the adaptive Runge-Kutta method. So we did hand code this equation, this method, but we can just use some solvers in Python to do one of these. So the one I'm going to use for doing this simulation is known as ODE int. Okay. ODE int in Python, and I believe it does the adaptive Runge-Kutta. So the way this works is we first need to define a function for which returns x double dot y dot, and then we call ODE int. So the call to ODE int will look something like this. Projectile RHS, and I will just write what the RHS means. I have to pass in the initial values, z0, the time span, all the timestamps, and then any arguments. In this case, the arguments would be examples of arguments would be whatever parameters which remain constant. So for example, in this case, mass, gravity, the drag force, times at which we need data. This is the initial condition. So initial condition in this case would be x0, y0, x0 dot, y0 dot. And then this last function is the right hand side, which we just wrote down. So it should return the rate of change of x dot, x double dot, y dot, y double dot. Okay. X double dot we wrote down as minus c divided by m x dot times x dot square plus y dot square, and y double dot we wrote down as minus g minus c divided by m y dot square root of x dot square plus y dot square. Okay, so let's see how this function is executed in Python. So I wrote this code which will basically integrate the equations of motion and simulate the system and animate it. So that was a bit fast. Let me just increase the slow down the animation. So this is the path followed by the projectile under the effect of drag. If you remove the drag, then you'll see the regular projectile equation, which doesn't have that kind of behavior. So let's look at this code. Okay, this is where my main loop starts. Before that, there are functions. I define initial position, initial velocity along the x, initial velocity, initial position in the y direction, initial velocity. Then I want to do this from 0 to 5 seconds. So then time, I use linspace to go from t0 to t end. I initialize the initial condition, which is going to be x0 dot, y0 dot. And then this is my call to the integrator, which basically calls the function projectile. The inputs are initial condition, the time, things, and then the arguments mass, gravity, and now let's see what this function looks like. So this is projectile. The inputs are z, t, m, j, and c. Now z is the state, which is the position velocity at that instant of time. T is the time, m, g, and c are parameters. So I unpack the velocities, which is the first and the third variable. And the second is in the 0th and second would be the x and y. I write the velocity magnitude. I find the drag force. And this is my equations, which I wrote down earlier, x double dot. X. And put on the d dot. And then this one is d dot. Okay, and then I return that as dz dt. And x dot ax, any y. And then there is the routine to animate, which is very standard. I take the data, I interpolate to get uniform data samples, and then I just make a plot of the projectile, the red dot, and then the trajectory too. Okay. That's how the animation looks. And you get interested by changing the drag force to 0, and you see that it's like the regular projectile. You can actually check that quickly. Let's go to where the parameters are defined, which is right here, and then change this to 0. And so now it's the regular projectile without force. It actually goes, if you prepare for more time, we'll see that it actually follows the parabolic path.